Hi everyone, we are from the Mobile Perception Lab at Shanghai Tech University. It is our great pleasure to be here to introduce our latest work, Globally Optimal Event Camera Motion Estimation. An event camera outputs a sequence of events denoting temporal logarithmic brightness changes above a certain threshold. An event consists of pixel location x, timestamp t, and polarity s. Event cameras perform well in high dynamic range conditions and have high temporal resolution. However, the special form of the input data requires new algorithms for their processing. Our work relies on Gallego et al.'s contrast maximization framework, which optimize image warping parameters such that the warped events exhibit maximum alignment, also called contrast in a reference view. In some cases, the image warping parameters are directly linked to the camera motion, most notably in any situation that can still be described by using a homography. Examples are given by purely rotational motion or motion in front of a planar scene. The contrast maximization framework may therefore be applied in a variety of scenarios, such as optical flow estimation, motion segmentation, motion estimation, and 3D reconstruction. Gallego et al. And Stoffregen et al. Presented and analyzed more than 20 objective functions for the contrast maximization, including the variance, the sum of exponentials, the sum of squares, the entropy, and so on. Here, we present the object function over sum of squares as an example. We process events in temporal order, where W stands for the warp function that warp the case event with a timestamp tk to the reference view by using the motion parameter theta. We find the nearest integer pixel location in the reference view and increment its value by 1. As a result, we count the number of the warped events for every pixel Pij in the image, which forms the image of warped events, IWE in short. To conclude, we sum up the square of the intensity in each pixel in the IWE to obtain the loss Ln. Optimal parameters will maximize Ln. However, existing methods rely on iterative local refinement, which is prone to fail if no good initial guess is given. This is especially the case as contrast maximization is generally a non-convex problem. Our core contribution is globally optimal contrast maximization using branch and bound as an optimization technique. The solution space is subdivided into branches for which we only need to compute upper and lower bounds for the maximum objective value. We derive novel upper and lower bounds for 6 different contrast functions as objectives. They are evaluated recursively and thus very efficient. For the lower bound, it is readily given by evaluating the contrast function at an arbitrary point on the search space. Here, we use the interval center θ0. Moreover, we present a recursive rule to efficiently evaluate the lower bound. With processing in the temporal order, the n+1's lower bound equals to the nth lower bound plus 1 plus 2 times the intensity of the n+1's warped location in the IWE. Here, we will show a toy example to demonstrate the idea behind this recursive lower bound. At the beginning, the lower bound L1 equals to 1, and the lower bound L2 equals to the lower bound L1 plus 1 plus 0, which results in 2. For the third event, the lower bound L3 equals to the lower bound L2 plus 1 plus 2 times 1, which amounts to 5. The upper bound can also be recursively estimated. Similar to the lower bound, the n+1's upper bound is equal to the nth upper bound plus 1 plus 2 times Qn. The bounding box frames all possible locations of the n-warped event in a subinterval big theta of the entire parameter space. Qn stands for the maximum intensity in the n+1's bounding box on the n's constructed IWE. As illustrated on the left as ground truth, there exist 4 events where 2 of them are warped onto the same pixel. For the first event at time t1, we calculate the bounding box and increment its pixel with maximum value by 1. Here, we choose the center of the bounding box since all the pixels have 0 value, and the upper bound for one event is 1. For the second event at time t2, we may again extract the bounding box and choose the maximum value to be increased by 1. The upper bound now is updated to 4. Similarly, for the third event at time t3, choose the center of the bounding box, increment by 1, and update the upper bound to become 5. For the fourth one, the chosen maximum in the bounding box will again be the initial accumulator, and the upper bound becomes 10. As required, it is bigger than the ground truth contrast of 6. With this strategy, we derive recursive upper and lower bounds for 6 objective functions. Note that the initial value L0 varies depending on the loss functions. We invite viewers to read our paper for the proof and further details. We apply the proposed algorithm to an AGV motion estimation with a downward-facing event camera. For this specific problem, the bounding boxes can be efficiently defined by exploiting the monotonicity of the trigonometric functions on the subintervals of the solution space. We evaluate the accuracy and the robustness of our proposed method GoCMF on simulated data. Figure A and B indicate the error distribution for angular velocity omega and the linear velocity v for both our proposed method as well as an exhaustive search strategy. Figure C and D visualize the average error of the estimated parameters caused by additional salt and pepper noise on the event stream. Results are averaged over 1,000 random experiments. Note that our proposed method has excellent robustness even for noise-to-event ratios up to 40%. In addition, we test our algorithm with all aforementioned contrast functions over various types of motions, including a straight line, a circle, and an arbitrarily curved trajectory. The objective function SOS-AAS works best, which stands for the combination of 2 objective functions, sum of suppressed accumulations and sum of square. We also include 2 traditional camera-based relative pose estimation algorithms, IFMI and GOVO, into comparison. In this figure, we see the estimated motion parameters and trajectories with our method and the 2 conventional camera-based alternatives. Our method performs best. We also compare GoCMF to local optimization technique. The optimization using local gradient ascent is evaluated by using different initial guesses. The trajectories are plotted on the top figure. It is clear that the local optimization depends on the initial guess, and it is outperformed by our method. Besides, we can confirm that our method is able to handle a large number of different ground floor textures, as shown below. To sum up, we first introduced our globally optimal contrast maximization framework and explained how to recursively and efficiently calculate the upper and lower bounds. Then, we applied it to the AGV motion estimation with a downward-facing event camera, for which recorded events experienced a frontal parallel motion in front of noisy, fast-moving ground textures. Our experimental result demonstrates its accuracy and robustness against several alternatives. Thank you for watching this video, and please feel free to visit our lab's webpage for more information on our latest research.